Hey everybody, and welcome back to Linear Algebra Online. So today I want to talk about this thing called spectral decomposition, which the movie Endgame basically threw this term into common knowledge now, because there's this ridiculous scene where Ironman is, also spoilers coming, pause the video if you want, but I'm going to say it anyways. But he's talking about the eigenvalue of a Mobius strip, and then he says something about like factoring in spectral decomposition or something. It's all just gobbledygook. Spectral decomposition is something I'm about to show you literally right now, and I literally don't know what he's talking about. I think they just got a math person, was like, hey, give us some math words, and we'll figure out a way to make it sound kind of cool. But my guess is it doesn't make any sense. So we are actually going to learn today about what this thing, spectral decomposition, is, and it's actually a very straightforward thing in linear algebra, so let's do it. So last time we saw that there's this thing, the Spectral Theorem, and that says that basically we can write a symmetric matrix in the form QTAQ equals D. And so that's like an orthogonally diagonalizable matrix. And this statement right here is also equivalent to AQ equals QD, or you could solve for A and get A equals QD QT, right? Because QT is Q's inverse, right? Vice versa, and so you can like just rewrite it, just like pull off those matrices and you can get this. And so if you start kind of unpacking all this a little bit, then A, right, I can write as, I'm going to write this as Q1 ... Q, we'll call it N, is like for an n by n matrix. So these Q's are just the eigenvectors from the diagonalization. So they're column vectors, basically, that are just the eigenvectors, okay? And then, so that's Q, right? And then D is just the diagonal matrix where you have the eigen values on the diagonal. And then you've got just zeros everywhere else. And then you have QT, right, which is just the transpose of that red matrix. So you're just going to get Q1 transpose, blah, 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 Qn transpose, okay? So if we, so I'm just basically going to get I'm going to rewrite A using just like matrix multiplication stuff, okay? So literally if you just do, if you multiply these two, let's do that first, you would get, let's see, what would you get? You get Q1 lambda 1, and then you would get Qn lambda n. It's just like because of matrix multiplication. And then I get all of that, still just copy down. And so then, just do rows times columns. You literally are just going to multiply this times this. You're going to put that here, and then you're going to do, down here, and then you're going to do the next one times the next one, right? And so on and so on and so on. So what we get here is Q1. We would really do like Q1 lambda 1, but we typically write this thing where we pull the lambda out to the right, because lambda is a constant, right? So whatever this one is, normally it would be in the middle, but we'll just move it over there. So then we go plus blah, 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 plus Qn transpose, lambda n. Okay, so this right here is actually what we call spectral decomposition. And basically it's just, a dot product of, it's just Q1 times Q1 transpose. That's all it is, right? And then times lambda plus so on, Q2 transpose times lambda 2, and so on. I think the spectral part comes from the spectrum of a matrix is, again, the set of all the eigenvalues. I think I said that in the last video. And so what we've sort of done here is we've decomposed A into this weird summation that involves the spectrum. So I think that's like where the name comes from. But I have no idea why this computation would ever be useful to figure out time travel. But for some reason it does. This is what spectral decomposition is, though. So I want to just kind of show you with a more contextual example of what it is, and show you kind of in this video why we might like it and why we use it and stuff like that. Okay. So what we're going to do here is basically what I remember doing with spectral decomposition. So its usefulness is actually in kind of the reverse direction here. So a lot of times we take this and we create A. So what I mean by that is, like, we might want to find a 2x2 matrix that has given eigenvalues and corresponding eigenvectors, okay? And so what this thing is going to do is going to give us a technique to build up the matrix A. So we'll kind of start here, because remember, these Q sub i's are just eigenvectors, right? So, and then lambda sub i's are eigenvalues. And so if we have those, it kind of gives us a way to build A out of eigenvalues and eigenvectors, which is kind of cool. And in a lot of real-world problems in linear algebra and stuff, and math in general, like, these are the important properties almost of a matrix, and they are linked to some sort of physical thing in the system. And so we might not actually need a matrix unless it does something specific with the eigenvalues or eigenvectors. So it's actually a very reasonable place to start to build up a matrix. So it's kind of an interesting trick, because I feel like a lot of times we have a matrix and we analyze it from there, but this is the first time we've taken the properties of some sort of space or something and built the matrix out of those properties. So this is basically what we're going to do. So we're going to build A where it's built out of its spectral decomposition. So lambda 1, Q1 transpose, plus lambda 2, Q2 transpose. So, and we are going to utilize one fact here. So we know that eigenvectors will be orthogonal for distinct eigenvalues, right? So, so long as our matrix is symmetric, I guess. So really, we're going to build a symmetric 2x2 matrix, okay? And so really the only thing we got to worry about is we got to make these vectors, so they're definitely like perpendicular, but we're going to normalize them also to satisfy all this stuff. So, so basically I need to normalize V1 and V2, and so Q1, so let me just, well, how about this? Q sub I is going to be V sub I over the magnitude of V sub I. So that is what I'll use in here, okay? So this whole thing that I just talked about here involves, an orthonormal matrix, and so I have the ortho part, but I need the normal part. So when I pop these in, they will be the normalized versions of these eigenvectors, okay? So A is going to come out of 3, so we'll just do it like this, 3 times Q1, which you can get just 3/5 and then 4/5. That's like V1 normalized. And then just times the row vector, 3/5, 4/5. So it's, Q1 transpose, plus -2. And then -4/5, 3/5 is V2 normalized, and then times by the transpose of that thing. Okay? And so if you just crank through this, right, you literally get a 2x2 matrix, okay? You would just get the 2x2 matrix, -1/5, 12/5, 12/5, and then 6/5. and notice that it is symmetric, okay? And that shouldn't be surprising because like we're just using the spectral theorem, kind of constructing a, in this fashion. So we're going to get a symmetric matrix. And just down here, I kind of said this before, but this becomes a very important technique because it lets you create a matrix with certain really important properties. And there's lots of times where what we want to have happen is like an eigenvalue of x or whatever x is and another one of y. And then we want like certain eigenvectors to have those scalars, right? And so then we have this spectral decomposition thing, right? And we can just pop in what we know, and we can get out a matrix that has those properties. So very, very, very common thing that I remember doing in like a lot of my higher level math classes. So I just want to take some time here and just do some other kind of examples related to orthogonally diagonalizable things. So this first one says that if A and B are orthogonally diagonalizable, would the sum be as well? So I don't want to go through like full-on proofs here. I just kind of want to give some intuition. So what I want you to kind of realize, anytime I say orthogonally diagonalizable, I'm basically also saying AT equals A, right? Or BT here equals B. Basically, it's symmetric, right? And so if you take, a symmetric matrix like this, right, then, I don't know, I'll just do something silly like this. So whatever's over here, right, is going to be over here like that. And then I add to it, so this is like my A, and then I add to it my B, right? Then, B is also some symmetric thing. I meant to put a plus in there. So I don't know. Like, we're just going to do circle. Not as fun this time. Just based on how you add matrices, right? You would add a thing here and add a thing here, like component-wise, right, in each spot. And so it's not hard to see that if you add two symmetric matrices, the next one should also be symmetric. So, maybe it's like something like, we're just going to say you get this triangle, and then something like that. But definitely the sum here, A plus B, this thing should still be symmetric, right? Yes. A plus B, the transpose of that thing should be A plus B. It is symmetric, and we know that symmetric is equivalent to orthogonally diagonalizable. So check, we're good. That is definitely true. If A is orthogonally diagonalizable, would A squared be? Or so on and so on and so on be? So for A being orthogonally diagonalizable, right, we know that A, we'll do it this way. So QA, we'll do it this way. I'm just going to go back because there's like three ways I can write this, right? And actually, I'm going to want this one here. So if A is orthogonally diagonalizable, then A equals QD QT. So A squared, which is equal to just A times A, is QD QT, QD QT, right? And then we know that these are inverses, right? So they're going to go out to the identity. And then you would just have QD squared QT. But D squared is still diagonal, right? So, yes. It definitely should be, right? If you square a diagonal matrix or cube it or whatever, you just square or cube or whatever the things on the diagonal, and so this thing still fits the structure of being orthogonally diagonalizable. So That's kind of a nice property of these things. Like if you get that one matrix is orthogonally diagonalizable, its square would also be. And so if you have two that are, its sum would be. And you can kind of mix these two together and things like that. Basically, there's a lot of properties and a lot of things work out nice with these. I remember getting to a point where it was like I worked with these a lot, and I just kind of felt like if I do general matrix arithmetic with them, they should stay orthogonally diagonalizable. And that's not always true depending on what it is, but it's always typically pretty quick to do something like this and kind of check whether whatever you have over here is still going to satisfy this kind of structure of QD, QT, or this structure or this structure. Any of those would be equivalent, right? Okay, so that's just kind of some intuition about those, a sum or a product. And for this one, I just wanted to go back kind of quick and just show that what we've been doing with the spectral decomposition and building a matrix extends really nicely to higher order matrices too. So this is probably the most important like computational thing that we kind of do in this section. Just knowing how we can build a symmetric matrix that has certain eigenstuff properties, basically. So we want these eigenvalues, and we want these eigenvectors to correspond to those, right? And so I just want to show you that there's nothing wrong with taking this thing and extending it out. Really the spectral decomposition is like an n-dimensional thing, perfectly nice. You can just keep adding in the structure of these terms. So if I do it with a 3 by 3 matrix, which is what I'm going to get here. So lambda 1 right there, and then Q1 is 1, 0, negative 1 normalized, which is 1 over root 2, 0, negative 1 over root 2. Then the transpose, so of that thing, 1 over, root 2, 0, negative 1 over root 2. And then I'm going to add to that eigenvalue of negative 2 times 1, 1, 1 normalized, which is 1 over root 3, 1 over root 3, 1 over root 3. And then times by the transpose, 1 over root 3, 1 over root 3, 1 over root 3. And then last but not least, I think I ran out of room here, 2 times, my lambda 3 times by negative 1 to negative 1 normalized, which is 1 over root 6, negative 1 over root 6, there we go, 2 over root 6, negative 1 over root 6. And then, again, multiplied by the transpose. And so that is like the spectral decomposition of a matrix A, let's call it, which should be symmetric because we're basically working with these orthonormal eigenvectors, right? And so then you just literally do out this matrix multiplication. This is a 3 by 1 times a 1 by 3. So you're getting a 3 by 3 plus a 3 by 3 plus a 3 by 3. And these are the kind of things like you can do on your calculator to speed everything up. I'm fine with that at this point. And so if you do that out, you get 1 6, negative 4 thirds, negative 5 6, negative 4 thirds, 2 thirds, negative 4 thirds, negative 5 6, negative 4 thirds, 1 6. And so sure enough, again, if you look at the symmetry on the diagonal, we have gotten a symmetric matrix. And this symmetric matrix, if you compute all the eigen stuff, it would be this stuff. It really is a super crucial kind of computation in linear algebra to, construct matrices that have certain eigen things, okay? These are really, really important characteristics, and they might represent, like lowest energy state of something, of a particle or something, or they might represent like the path of like least resistance in some force or something like that. And so what we do in a lot of sciences is we look for this, and we want to have certain things here, and then we use spectral decomposition. Perfectly fine in any dimension you want, you just have more things to add together. And then you'll build out your matrix from that. And then you can use this to do all sorts of other stuff or whatever. But it's a very important little computation, and just comes straight out of this idea right here. I'm basically just, here I'm just decomposing the little parts of these matrices, right? And then you just do out the multiplication. You can see that you can get this form of A like this, and that is what we call spectral decomposition, which again has something to do with time travel. And that's that.